Glad to have you here. We have seen that some functions have extreme values, whereas others do not. We don't always have an absolute maximum or an absolute minimum. For example, if we look at y equals x squared, that's a parabola, and there is an absolute minimum, but there's not an absolute maximum because it continues going up indefinitely. And so we want to know under which conditions will we have absolute maximum and minimum values. And we have a theorem that tells us exactly when we can expect them. If f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval from a to b. So basically, we need a function to be continuous, specifically on a closed interval, if we want to be guaranteed to have extreme values. There might be extreme values in other situations, but these conditions are enough to guarantee that we will have extreme values. Now, I want to look at just a few graphs. Let me take a moment to draw those. Here we have 3 examples of functions that are continuous on the closed interval from a to b, and we can see that each of these attain a maximum, an absolute maximum value and an absolute minimum value. If we look at the first one, we've got an absolute maximum value here and an absolute minimum value down there. In the second example, we have an absolute maximum somewhere around here, and then the absolute minimum happens to be an endpoint. And then in the third one, the absolute maximum, it looks like it's actually hit twice, which is totally possible. Doesn't have to happen only once. It could get hit multiple times. And then we have an absolute minimum down there. And I'm going to give you 2 more examples, but these are examples where we don't have a continuous function on a closed interval. And I want to show you why, if we don't have those conditions, it's possible that we don't have an absolute maximum or an absolute minimum. Now, here are 2 examples. This first example, the function is defined on a closed interval. It's defined from this first x value, 0 actually, to whatever the x value is here, but it's not continuous. We have a break in the function, and in this case, we don't have an absolute maximum value because our graph gets closer and closer to that point, but we've got an open circle there, so that's not actually a part of the graph. So there is no absolute max here. And we have a similar situation with this other graph. Here, in this case, it is actually continuous on its domain, but it's not defined on a closed interval. We have an asymptote here, and the function is not defined there. So the domain of the function is closed on one side, but then open on the other side. And in this case, we can see that the function's getting bigger and bigger and bigger. And again, there's going to be no absolute maximum because it is asymptotically going up towards infinity. Now, there are certainly functions that are not continuous on a closed interval and still do have absolute maximum and minimum values, right? It's possible that if a function doesn't satisfy these conditions, it still will have an absolute maximum or an absolute minimum. That's possible, but it's not guaranteed. What this theorem says is if the function is continuous on a closed interval, then it is guaranteed to have an absolute maximum value and an absolute minimum value. And so if we're dealing with a function that is continuous on a closed interval, we know there's going to be an absolute maximum and an absolute minimum, but we don't know exactly how to find them yet. And there is a method that we're going to use here to find those absolute maximum and minimum values, and it is called the closed interval method. And I'm not just going to tell you the closed interval method word for word. I'm going to talk about what it is. We're going to kind of discover it ourselves. And the way that we're going to do that is we're going to look at these three graphs where we had a continuous function on a closed interval, and we're going to look and see where these extreme values happened, where these absolute maximum and absolute minimum values happened. Now, if you look at this first one, we've got an absolute maximum value up there and an absolute minimum value down there. And you might notice that these both happened at parts of the graph where we have horizontal tangent lines. So one possibility for global extreme values is where the derivative is equal to 0. If we look at the second graph, we do see one situation where that's the case. We've got a horizontal tangent line up there, but we also have a global extreme value, this global minimum, at an endpoint. So it's possible that an endpoint of a closed interval is going to give us an absolute maximum or minimum value. So we have to check those as well. And if we look at the last graph, there are a couple of places where we've got horizontal tangent lines, but there's one more place where we have an extreme value, and this is specifically at a place where the derivative is undefined. Right? Here we have a sharp point in our graph, so we know it's not differentiable there. Do you remember the name that we had for points where the derivative equaled 0 or the derivative was undefined? We had a name for those specific points, for the x values. Those were called critical numbers. Remember, a number is a critical number of a function if the derivative is equal to 0 or if the derivative is undefined. And those critical numbers are going to be one source of absolute maximum and minimum values, but the other source is going to be the endpoints here. And the closed interval method tells us that basically we need to check those points. So here it is, and we'll just reiterate. To find the absolute maximum and minimum values of a continuous function on a closed interval, first, you find the function values of the critical numbers, which is where the derivative is 0 or does not exist. Then you find the function values at the endpoints of the interval, and whichever is the largest of those is your absolute maximum, and whichever is the smallest of those is your absolute minimum, because those are the only places where an absolute maximum or minimum can occur when we have a function that is continuous on a closed interval. Let's look at one example, and then you can look at a few more in the practice videos if you'd like. Find the global extreme values of f of x equals x cubed minus 3x squared plus 1 for x between -1/2 and 4. Now, before we use the closed interval method, we have to make sure that this function satisfies the requirements for that method to work. Specifically, we need it to be continuous on a closed interval. Now, this is a polynomial, so we know it's always continuous, and we're told that we're looking on a closed interval, so that does satisfy the requirements. And the first thing we need to do now is find the derivative, because that is how we're going to find our critical numbers. So if we differentiate this, the derivative of x cubed is 3x squared, and then minus the derivative of 3x squared is 6x, and the derivative of 1 is 0. So this is the derivative, and for the critical numbers, we need to know where this is equal to 0 and where it's undefined. Now this is always defined, so we don't have any critical numbers coming from that, but we can set it equal to 0 and solve. To solve this equation, we can factor out 3x, so that's 3x times x minus 2 equals 0. And if we set both of those factors equal to 0, we get x equals 0 or x equals 2. Now we want to make sure that those are in our interval, and both of them are. So what this means, the closed interval method, it means we need to check the function values at those critical numbers, x equals 0 and x equals 2. We also need to check at the endpoints x equals negative 1/2 and x equals 4, we need to plug those into the function, and whichever of these is the largest function value, that is our absolute maximum, and whichever one is the smallest, that is our absolute minimum. So we need to evaluate this function at 0. Well, if we plug in 0 for everything, only the constant term isn't 0, so we end up with 1. That's pretty easy. Next up, we plug in 2. That's our next critical number. And if we do that, 2 cubed is 8 minus 3 times 2 squared. 2 squared is 4. 3 times 4 is 12 plus 1. 8 minus 12 is negative 4 plus 1 is negative 3. All right. Now x equals negative 1/2. All right. Negative 1/2 cubed is negative 1/8. And then minus 3 times negative 1/2 squared. Well, negative 1/2 squared is positive 1/4. And negative 3 times positive 1/4 is negative 3/4. And then plus 1. And so we've got 1 minus 3/4 minus an eighth. 1 minus 3/4 is 1/4. And 1/4 minus an eighth is 1/8. So we've got 1/8 there. And then we also have to evaluate the function at 4. 4 cubed is 64 minus 3 times 4 squared. That's 3 times 16, which is 48, plus 1. 64 minus 48, 16, and 16 plus 1 is 17. And so if we look at these, the largest of these values is 17. So this is our absolute maximum value. And the smallest of these is negative 3. So this is going to be our absolute minimum value. So if we wanted to state things a little bit more clearly, the absolute minimum value is equal to negative 3, and it occurs at x equals 2, one of the critical numbers. The absolute maximum value is 17, and it occurs at x equals 4, which is one of the endpoints. So we can see here, it's not always the critical numbers, it's not always the endpoint. It can be either or, so that's why we need to test all of the critical numbers and both of the endpoints, and that will give us an idea of what the absolute maximum and absolute minimum values are.